Last time we looked at the derivative of y equals e to the exponent of x. So what happens if we change the base to any other number besides e? Well, let's determine the derivative using first principles for y equals 2 to the exponent of x and see what happens. So remember, we have the limit as h approaches 0 of f of x plus h minus f of x all over h. And that gives us the limit as h approaches 0 of 2 to the exponent of x plus h minus 2 to the exponent of x all over h. Following the same procedure as yesterday, this is the limit as h goes to 0 of 2 to the exponent of x times 2 to the exponent of h minus 2 to the exponent of x all over h. So let's factor out the 2 to the exponent of x, and we're left with the limit as h goes to 0 of 2 to the exponent of h minus 1 all over h. Now remember, we can take out that 2 to the exponent of x and place it outside the limit sign because there's no variable h in that term. Now again, if we use direct substitution for this limit, we get the indeterminate form, and this means that the limit may exist. So we're going to estimate this limit using the table of values. So we're going to test it as h approaches 0 from the left and h approaches 0 from the right. So let's take some h values in both scenarios. So take a moment now and determine what 2 to the exponent of h minus 1 over h equals for each of the following values. And if you look at what we have here, they appear to be approaching a number approximately equal to 0.693 something. And if we did one more of each of these, you would end up with 0.6931 and 0.6931. If we're trying to evaluate this limit to 4 decimal places, we can see it's approaching 0.6931. So what does that mean? That means that this limit here is approaching whatever this number is. So we have that our derivative f prime of x is equal to 2 to the exponent x times 0.6931. That's the same for all other powers with a base other than e. Let's take a look at 3 to the exponent of x. Well, I'm going to do this one for you. You're going to discover that if you followed the same method, you'd end up with a derivative of 3 to the exponent of x times 1.0986. So notice this one approached a different number. So the question is, what is this number and what is this number? How can we get it? If we want a shortcut, we need to determine the pattern that is occurring here. So for this derivative here, f prime of x is 2 to the exponent x, and that number 0.6931 so on is actually the natural logarithm of 2. And similarly for this one here, f prime of x is equal to 3 to the exponent of x, and that number 1.0986 is the natural logarithm of 3. So hopefully now you're starting to see a pattern here. So if I was to give you, let's say, f of x equals 4 to the exponent of x, what would the shortcut be for this power? Well, you should say 4 to the exponent of x times the natural logarithm of 4. So therefore, given the function f of x is equal to the power of base b raised to the exponent of x, then our shortcut for the derivative, f prime of x, is going to be equal to b to the exponent of x times the natural logarithm of our base b. So here is the shortcut for all exponential functions. Let's go through some examples and see what we get. So first one, y equals 7 raised to the exponent of x. Well, that means that dy dx would be equal to 7 to the exponent of x times the natural logarithm of 7. And we're done. Next one is a composition of functions. So we have f and g. So f is 7 to the exponent of x, And g is x squared. So f prime is 7 to the exponent of x, ln 7. And then g prime is just 2x. So this derivative, g prime of x, is going to be 7 raised to the exponent of x. But in this example, it's a composition, so this would be 7 to the exponent of x squared times the ln of 7, then times g prime of x, which is 2x. All right, next one. So again, this is a composition of functions. So f prime of x, it is 5 3x squared minus 2x times the ln of 5. Since this is a composition of functions, we need to multiply by the derivative of the inner function. So in this case, we have 6x minus 2. All right, next one. Notice in this example, we have a function times a function. So we're going to need the product rule. So we have h prime of x is equal to, so p prime q. So this is 3 times 5 to the negative x squared plus 3x, so p q prime, times the root of 5 to the exponent of negative x squared. So that'd be 5 to the exponent of negative x squared, then times the ln of 5, but then times the derivative of the inside function, so times negative 2x. This one we can actually simplify a bit. There's a common factor of 3. There is a common factor of 5 to the exponent of negative x squared. So let's take those out. So we have 3, 5 to the exponent of negative x squared, and then what do we have left? We have 1 plus, so this is gone, this is gone, the 3 is gone here, this is gone here, so it's actually minus 2x squared, that's from here and here, times the natural logarithm of 5. And the last one, in this one we have a function over a function, so we're going to use our quotient rule. So our quotient rule gives us the following: dy over dx is equal to, well, the derivative of the numerator is e to the x squared times 2x, then times x squared, so p prime q, minus p, so e to the x squared, times q, times 2x, all over x squared squared. So this gives me in our numerator, that's 2x cubed, e to the x squared, minus 2x, e to the x squared, all over x to the 4th, and we can now common factor. So this gives me 2x e to the x squared is my common factor in the numerator. That leaves me with x squared minus 1 all over x to the 4th. And again, what do? We cancel this and this. We took out the 2x and we took out the 2 and the x here, which gives us x squared. And the last thing, we could cancel out the x's here, and we are left with the following derivative. dy over dx is equal to 2 times e to the exponent x squared times x squared minus 1 all over x cubed. Example 2, determine the equation of the tangent line at x equals 1 for the following function. So to find the slope, we need the derivative. So f prime of x is going to help us find the slope of this tangent. This is the same as example 1c. So the derivative of 5 to the exponent of 3x squared minus 2x is 5 to the exponent of 3x squared minus 2x times the natural logarithm of 5, then times 6x minus 2. So we want the slope at x equals 1. So we want f prime at 1. And that's going to give me 5 to the exponent of 1 times the natural logarithm of 5, and then times 4. So this tells me that my slope is equal to 20 ln of 5. So there's my slope. But now we need a point. So let's get the point. So our point of tangency we know is at 1 and something. So all we do is sub 1 into our function. So f at 1 is equal to, we put that into our expression, 5 to the exponent of 1. So therefore the point of tangency is 1 and 5. So now we know we have the following, that y equals 20 ln 5 x plus b, right? This is mx plus b. We're going to sub our point 1 and 5. So 5 equals 20 ln of 5 times 1 plus b, and therefore our y-intercept is equal to 5 minus 20 natural logarithm of 5. So let's state the equation of our line. So y equals 20 times the natural logarithm of 5, x, plus our b value. And our b value is 5 minus 20 natural logarithm of 5. And we're done. Notice I did not need a calculator. I just kept everything exact. Example 3. Determine the values of x at which the tangent to each curve is horizontal. So let's do that. So notice 3a is the same as example 1d, and we already discovered that that derivative, h prime of x, was equal to 3 times 5 to the exponent of negative x squared times 1 minus 2x squared ln of 5. All right, we're going to let h prime of x equal 0. So we let h prime of x equal 0, and therefore we end up with the following. 0 equals 3 times 5 to the negative x squared, 1 minus 2x squared ln of 5. I'm going to set each factor equal to 0. So we have 5 raised to the exponent of negative x squared. We already know that can never equal 0, because that again is an exponential function, which looks something like this. And then for the second one, we're going to let this equal 0. So I have 1 minus 2x squared natural logarithm of 5. That I want it to equal 0. So let's rearrange. So I get 2x squared natural logarithm of 5 equals 1. Then I get x squared equals 1 over 2 natural logarithm of 5. And then I'm going to square root that. So I'm going to get x equals plus or minus 1 over 2 natural logarithm of 5. So there are the x values where that function will have a slope of a tangent equal to 0. And the last one, b. So again, from example 1e, we determine that dy over dx is equal to 2e to the x squared times x squared minus 1 all over x cubed. So if dy dx equals 0, then we end up with the following. That 0 is equal to 2 e to the x squared times x squared minus 1. So e to the x squared, we already know, cannot equal 0. Again, that's because we have an exponential function in which the range is always greater than 0. And for the second factor, that's x squared minus 1 equals 0. That means x is equal to plus or minus 1. So again, there are two values. There are two locations on this curve where the slope of the tangent equals 0. All right, so in summary, if we're given the function f of x is equal to base b exponent x, then its derivative is base b exponent x times the natural logarithm of b. So if you're given f of x equals b raised to some exponent of g of x, then f prime of x is b exponent g of x times the natural logarithm of b, but then again times the derivative of the exponent or the inside function, and that will be g prime of x. If you have any questions, please let me know. Then attempt the following questions from your textbook, and good luck.